So this is the second lecture of 2160, Identification, Estimation, Learning. And we're now actually studying part one, the regression, focusing on least squares estimations for deterministic systems. For some of you, regressions is rather unfamiliar terminology. Originally, it came from biology. Someone examined the height of many peoples, and it turns out that if parents are taller than the average height of the people, then their children tend to be shorter, going back to the average height or regress to the average. Now, the concept has been extended and generalized. Now, it is a statistical method for examining relationship between multiple variables. In particular, we look at the case to find the influence of independent variables to the dependent variables. Now, if the data are actually given by these blue dots, we don't chase individual data points, but we like to grasp the general trend which may be approximated by a straight line like this, and that this can be parameterized in this way. So, U is basically independent variables, and then Y is dependent variables. This notation sounds the flavor of system dynamics and control. The U is the input and the Y is the output, but we treat much broader the systems. And here we have two parameters, B and C. These are parameters we like to determine so that it can best represent the these data. Now, just a mathematical trick, we like to use this homogeneous form. Although we have just one independent variables, but artificially we create the second variable, the U2, which is to take the value of 1 all the time. Then this expressions with this constant can be expanded to this homogeneous form. In general, we deal with this type of linear homogeneous equations where U1 to M are actually independent variables, and then B1, B2, Bm are parameters involved. And in systems and estimation theory, we often use the vector theta. We combine all the parameters to estimate B1 to Bm. Therefore, theta is m-dimensional, the vector. Accordingly, we like to put the U1 to Um into m-dimensional vector. It's called a regressor. And it turns out that this expression can be viewed as a linear, inner product between these two vectors, theta and phi. So you can write it, C transpose of phi, and that is to take the inner product of these two vectors, or equally, we can write it, to take the transpose of this phi transpose theta. We call this a linear regression. And the problem is that first we collect the data, independent variables or regressors, and output observables or dependent variables, Y's. And the data may be numbered from 1 to capital N, and N is sufficiently large number. And based on this set of data, we like to find the best parameter values of theta. That's a problem that we like to discuss today. Now, that particular equations on the linear regressions, it sounds very much specific, narrow model, and it sounds a static relationship. But in fact, it can represent a dynamic case too. So think about a simple linear time invariant systems. you can, you have learned, say, something like, differential equations, ordinary differential equations, or converted to transfer functions, or input-output relationship also, and it can be represented by impulse response. So you put the one impulse at a certain time, and then observe the output, which shows this kind of a curve, right? And the great thing with this impulse response is that even though input u is some complex time function, but we can predict the y by taking this kind of integral called convolution, u t minus tau multiplied by g tau. And in case we have discrete time systems, we sample this, and the g tau 2, we sample it, g sub 1, g2, something like this. And this integration is reduced to summation like this, right? Now, I think you can recall the convolution, but I know physical sense of this is that suppose we like to see the output to yt at the time t equal t, and then this systems, is basically driven by some time function u, time series input coming into this system, not just a single one impulse, but in a series of impulses coming to this system. And then kind of value yt reflects all the previous inputs coming to this systems, but depending on when that input came to this systems, it is to have different influence on this. It's basically weighted to sum of the previous inputs. Now, how we weight is basically based on this impulse response. At the one time step back, input was this much, and impulse response, the first value is G1 like this, and then this one is multiplied to this, and that is part of yt. If k time step back, we had this large input ut minus k. The influence of this on the current by yt is somehow attenuated because this is odd, k step odd. How much is attenuated? It is governed by this impulse response at the k step later. This impulse influence this much. So we take the k time step backward, and then we take the gk multiplied by this, and then that's a part of this yt. So this is weighted the sum of this input sequence is to give the yt. Now, if the system is stable, this impulse response goes down to 0. So we can truncate it at a certain point. It turns out that this one is not the infinite summation, but a finite summation. And we can write it perhaps in this way: yt equal g1 ut minus 1 to gm ut minus m. So what is this? Yeah, this one is exactly linear regression. By putting together, oops, this is theta, I should change this one to a g1 to gm, silly mistake, sorry, this one g1 to gm. And then regressor, we take a ut1, ut2, ut minus m, put in this one in this way. This expression, finite impulse response, is given by this, inner product between the two. Okay, it's called a finite impulse response, FIR model. So given some observation of data, input output, oftentimes we like to find these actually, coefficient G1, Gm. That's one of the typical, system identification program. So in fact, this form, you can see it in many ways and in many applications. Let me take another example. So here, yt is obviously a nonlinear functions of x1 and x2. So, it looks like not the linear, situations, But let's see, oops, sorry. Yeah, we have input, output like this. And then the curve is something, it's really nonlinear. In this case, we have two variables. So x1, x2, and I have to draw one more curve. And this one is kind of in a curve, like this, right? So it is actually a nonlinear relationship, but if you look at this, parameters to identify versus, rest of the part, relationship is linear. In other words, parameters B1 to B4 are linearly involved in this expression. So to highlight this, let's define the regressor to be x1, x1 cubed, x1, x2, and then exponential minus 3x1, putting here in this four-dimensional vector. Then actually parameters in B1 to B4, just the inner product between the two gives you this yt. So, given some data, x1, x2, and y, many data are obtained, then we can find the best fit parameter values of B1 to B4, the same program. I have just released the PS number program set number 1, and you will find other examples of nonlinear and or dynamic systems where unknown parameters are linearly involved, linear in the governing equation. And yeah, obtaining the unknown parameters from data can be treated as a linear regression problem. Okay, we can solve it. Okay, now, so how we can find the best fit the parameters? Then we introduce the prediction error formalisms. It's shown with this in this kind of schematic block diagram. Here, real systems and the models are existing, and input or regressor phi t fed into real systems, and you have some sensor to observe the output to yt. Okay. At the same time, you have a model in which you have some parameters, theta, involved. So based on the your estimate of parameter theta, you can produce some output y hat. And based on these two, what's the real measurement, the other is an estimated one, you see some prediction error. And then you can see that, well, if the model structure is correct, if you see error, that should be caused by some inappropriate value of the parameter theta. So you can find the theta so that this error may be reduced. And we do this for many data points and then find the theta value that fits best to the actual data. This is prediction error formalisms. And you can see almost exactly the same diagram in observer, in Kalman filter, and the system identifications, and even learning a problem. You see this, on framework repeatedly. So this is very basic stuff. So what we'd like to do is that, oh, by the way, you see here we have a hat. So if you see a hat on top of the variables, that means prediction, your estimate. It's not the really physical one. It's a variable that's sitting on your computer, not the real one. Real one doesn't have any hat over here. So the difference between real measurement and the prediction is this prediction error. And then what we like to do is take the square of them and then take all summations for all the samples t equals 1 to m. I use a t here, but a t does not necessarily mean the time t, but it's just an index. It can be treated in actually a broader way. Okay, so suppose we have capital N samples. We take the summations and divide it by n to get the mean squared error, right? So what we'd like to do is actually least squared estimate, or LSE for short, provides the parameter vector that minimizes the above mean squared error. So we write theta hat least square equal argument to minimum of v and theta. Maybe some of you haven't seen this mathematical notation ARG. This represent the argument of the functions here, and what we'd like to do is to minimize this with respect to theta and pick that argument to theta that is actually the left-hand side. Okay, so how do you find the minimum point? And this is the mean squared error, and it is a function of theta. And what we'd like to do is to find the particular value of theta that is to minimize this. So what sort of a technique do you come up with? Well, many of you think about just to take the derivatives and then set them 0, right? That you are exactly right. Yeah, so we take the Vn is actually some scalar function, and then we take the derivatives with respect to theta and then set it to 0. This is the necessary condition for Vn to take a minimum value, right? Now, one critical point here is that now we are taking the derivatives of scalar functions with respect to the vector variable theta. So yeah, maybe some of you never seen the scalar function differentiated with respect to a vector, but don't worry. This is basically, you can treat it in the same way as you do, scalar by scalar differentiation. So the theta is a vector, but you can do it component by component. For instance, let's pick the ith component, theta I. So partial Vn or partial theta I, right? Let's see this guy. We have Vn, here, y hat minus y squared. Let's replace this one by capital XT. And so this guy is 1 over n summation capital XT square, right? So by applying the chain rule, Vn differentiated with respect to capital XT first, followed by XT of to theta I. So from here, it comes out to 2 capital XT, and then we need to examine this guy, partial derivative of capital XT by theta I. So if you look at the XT, that is this guy. And theta is involved only in the first term. The second term is just a measurement. It's not actually dependent on any theta. And if you look at the y hat the t theta, it is basically a linear regression. So it's actually, if you write it component-wise, this is the inner product component-wise expression, right? And then here theta 1 is the first element component of the vector theta, and then phi 1 is the first element of the regressor, right? So you remember this expression. And what we'd like to do now is differentiate it with respect to theta I, this guy. So only phi I remains. So this particular part is phi I t. Simple. So the result, partial Vn, partial theta I, we put back xt right here. So y hat minus y times phi I t, right? Now, if I is 1 and partial Vn, partial V1, this remains the same. We should get the phi 1. If on I equal m, we should get the phi m over at this point. So we can collectively write this guy in this way, and then this one is basically related to the first expression, scalar function differentiated with respect to the vector quantity. And we set all of these 0. So this is not just a scalar 0, but vector 0. and then that can be written in this way, right? Phi 1 to phi m is basically vector phi. Okay, so that is the necessary condition for minimum and optimum estimate. Okay, so I just wrote the same equation here from the previous slide. And please recall that this y is this inner product. I now break this guy, distribute this phi t. We get the two expressions, yt phi t, and this side, phi transpose the theta, and then the phi t. Okay. Now here's the trick we have to make. So if you look at this guy, this one is nothing but the inner product. So the result is a scalar quantity, right? Scalar can be placed anywhere, all right? Scalar times the phi t is the same phi t times that the scalar, right? So let's move this one over here. Then maybe we can check the dimension of this multiplication. So phi t is m by 1, right? And then phi transpose is 1 by m. And here theta is m by 1, right? So you see this three vector multiplication is consistent in terms of the dimension, m by 1, 1 by m, m by 1, right? So we can apply the associative law to this. So put the parentheses here, and we multiply this first, followed by multiplication with the theta. That means that we can factor out the theta from this expression, leaving this part to be m by m matrix. Okay, so phi transpose, and then right-hand side is output or dependent variable, yt times the regressor phi t. Okay, we take the summation over, t equal 1 to n. You see this kind of equation quite often. It has a nice name, a normal equation. A normal equation. Now, phi t times phi t, transpose is n by n matrix, right? Let's assume when we take a summation, this one to be non-singular. This one is non-singular. Then we can directly solve this one for theta. So, this phi transpose summation inverse times the right-hand side yt times phi t. This is the solution to the least the square. Now, I have a couple of remarks on this. First of all, I just said that this one to be non-singular. But what that means? What it means? Well, each phi vector is m-dimensional vector. So if you plot this one in m-dimensional space, so phi 1 is the first component, the phi 2 is the second component, the phi m is the final component, m-dimensional space. And each of these actually, given vectors point in certain directions, right? So if you collect the data, phi 1 to phi n, in a very nice way, so that you basically span this one in all directions in the m-dimensional space, you can basically span this whole m-dimensional space. This matrix becomes non-singular. If instead, for some reasons, these vectors are all aligned within a hyperplane over here, not actually, the direction and perpendicular to that hyperplane, the set of phi 1 and phi n vectors do not span the m-dimensional space. If that's the case, this one becomes singular. So when you do data collection, you must make sure that you are poking all the direction. You get the rich combination of data must be taken. We assume that in here. Okay. Second remark, when the m by m matrix is non-singular, we get this, it's actually a unique solutions, right? There's no ambiguity, no second best and third best or whatever. It is actually the optimal one, just a single solution. And this is a very strong conditions. And, and sometimes, that is not the case. For instance, I plot this guy in the, parameter space, theta 1 to theta m, and versus Vn plotted here. And in this case, you have just a single minimum point over here, it's easy to find. But instead it goes and this, and then a little bump over here. It's very confounding. You may, just a necessary condition for optimality, you may actually pick this particular point, which is not the global optimum, right? So that's actually a local, it's nothing but just a local, minimum. So, we like to solve the problem in this way. It's basically, we find the global single minimum point. And if the formulations are being made in this way, that's very convenient in many ways. So this convex optimality is one very good features. And so far, this least square estimation has done this very nicely. Okay, now okay, now before going further, any suggestions or questions, things that you want to clarify? Are you okay? I just slow down. Every step is very slowly, so it should be all right, I hope. Hi, Charles.
That I have. Hi.
Go ahead.
So how would you deal with a situation
I
where,
don't
say,
hear
you
you for some reason, sir.
Oh.
We can hear you, Charles. I think there might be a volume issue on Professor Asada's end.
Okay.
Nick, we have a technical difficulty. We don't hear Charles. Okay.
I can
chat.
I'll type in the chat.
Okay. So one question, Charles, is actually, is this necessary conditions also sufficient for linear model? So just recall the remark two. Remark two, that's actually convex optimization that's guaranteed to be the optimum necessary and is sufficient. So I can't hear him. Oops. Oops. You don't hear me? Some of you do not hear me? Okay. Okay, we can, okay, that's all set, right? Okay, so it should be all right. Technically, it's okay, right? But if you have a physical system with non-negative control inputs, how would you get your regressors to spin? Yeah, that's actually a little bit high level question. Yeah, so there's a special areas that actually you have only positive side, and then we take a little different techniques in doing that. But in this particular case, even though the things are positive, if the vector is actually visiting all the actually directions, or all the direction means that all the independent vector directions, and it should be all right. It is all right. Yeah. So direction is a little bit confusing. It's not the plus minus direction, but independent vector the directions. Okay, so let's go back to slides. Yeah, this guy. So, so far, these square algorithms, you just collect all the data and then, put into this equation, so you find the optimal ones, right? But in this case, you have to collect all the data first, then do this, processing. But what we are interested in other situations, and how about the time sequence data? So, many data points have shown up, and then actually at the time t-1, we get the series of data, and then we found the best fit, blue line over here. Okay, so this is the best, include, up to and including time t-1, all the data. But at the time t equal t, a new data comes in, and including this guy, we need to change this best to fit the curve to a little bit of different directions over here. Okay, so at the time of t plus 1, we get the even another new data, and then we need to change this curves again. So in the actual real-time control setting, we have to deal with the time sequence data, right? So instead of waiting at the end of the sessions, we like to get the some best estimate based on the observation up to that point. So that is a recursively square algorithms. Yeah, this is exactly the problem in the early 19th century. Carl Friedrich Gauss did it in his actual planetary observation problem. Nightly, he got the new data here, and they have to change the some curve fitting. And he's a smart guy. Do I need to do this? Is there any better way of doing that? And it turns out to be recursively square algorithms. So at the time t-1, after this t-1, and including this time t-1, we have collected all the data, and this theta hat t-1 is the best estimate. Okay, now we get the new regressor, and then dependent variable and observations just obtained. Based on this, how we can actually update or correct this estimate to this new estimate, theta hat t. Okay, do I need to solve the entire problem from scratch, or is there any way smarter than this, such as we actually based on the previous best estimate and add some correction term, or update the term based on phi t and yt? And this is what we like to do, and this is the second half. Okay, so here's our goal. Okay, but the point is that even though we make this kind of correction, corrected one must be the optimum solution. So this guy must satisfy this expression. This is actually the batch processing technique up to the time t. This kind of recursive one must provide the same results as this. Okay, so that is a problem. Okay, now let us derive the recursive formula to update the estimate with the new observation phi t and yt. So now we assume that the enough data are initially available in the following derivation, so that the matrix, this guy, phi transpose the summation over I equal 1 to t-1. So this is the type of t-1 is non-singular. And actually we defined pt to be the inverse to it. It's non-singular. It's actually we take the inverse to it, and then the bt is given by this. So if we multiply these two, it's basically this guy. So simply pt bt. We just replace these for the purpose of the following derivation, but please remember that the bt is the output dependent variable observation yt times regressor phi. okay? And a P is a regressor, it's, transpose M by M matrix, okay? Just a product between the two. So first step, we'd like to actually divide this guy, BT, into the one that you have already obtained at the time t minus 1 versus a new one. Okay, so what you need to do is just take summation, stop it at the time t minus 1, leaving this one alone. And this particular part, by this definition, is nothing but the BT minus 1, right? And this guy is a new observation. Okay, and the PT, inverse, if you take the inverse again, it becomes phi transpose this guy, and we can actually separate the new observation from the previous one. So this particular part is the PT minus 1 inverse, and then a new addition. Okay, so update of BT is straightforward, but the PT is difficult. And then the inverse of the M by M matrix must be computed in doing this, right? And do we need to take the matrix inversion every time recursively, every step? Do we need to do that? In fact, compute the matrix inversion, the computational complexity is actually the dimension M to the cube. So it's actually heavy computation, okay? Now, a very neat thing is that we don't have to take the, inverse every time you do this M by M matrix inversion. We use this, matrix inversion lemma, and this is the key mathematical technique involved in this recursively squares. So I just wrote the previous, the last line, PT inverse. This is actually summation phi transpose, right? So now we first pre-multiply PT. Pre-multiply means that the PT is multiplied to this term from the left. And also, post-multiply PT minus 1 to this equation 12. So post-multiply PT minus 1 from here. Okay, so the first one becomes PT inverse, PT minus 1, right? We do the same for the right-hand side. First, this guy becomes this, and then this becomes this, right? Now, obviously, these two canceled, and these two cancel. So we got this equation, so right? So PT, just before the PT equal PT plus something like this. To that, we further post-multiply phi t from the right, post-multiply here. So PT minus 1 phi t, PT phi, and then here PT phi t transpose PT minus 1, and then I put the phi at the last, this position, right? Now, if you look at the this product, phi transpose PT minus 1 phi, check the dimensions. This is 1 by m, m by m, m by 1. So as a whole, this guy becomes, well, what is the dimension of this? It's just 1. It's a scalar, right? Scalar. So when you actually factor out the PT phi from here, this is scalar, and so this particular part is 1 plus something. So this as a whole becomes scalar. So, scalar, it's no problem to divide both sides by the scalar quantity in terms of the computational complexity. This is nothing. So, we divide both sides by this, then it turns out that the PT phi t, PT phi t equal, this one going to the denominator, is expressed by this. So what is the physical sense of this? Yep. We need to do one more step, okay? One more step. Post multiply phi t PT minus 1. Okay, so look at this. We are very close to find the PT as a function of pt minus 1. One more step is needed. So we post multiply this guy, comes to this point. So yeah, you know, let me just put this guy, putting this one over here, also putting this one over here, right? Over here. So, you know, the left-hand side, this term, pt phi t, times, you know, phi transpose, pt minus 1. We get this expression. We have found this somewhere previously. See this equation 13, this is exactly the same term as this, right? And remember that these two cancel out, you know, this, you know, cancel out. So this guy is nothing but, you know, pt minus 1 minus pt, or this term, pt minus 1 minus pt, right? So left-hand side, you know, this guy, that's replaced by pt t minus 1, and moving the, you know, pt minus 1 the other direction, you get this expression. The remaining part is this. So this denominator are the same. And the numerator, we multiply this from this side. So that results in this expression. Very the confusing equation, but I know if you examine this more carefully, the right-hand side of this expression is all about the pt minus 1 and the phi t, nothing else, right? And the left-hand side of pt is obtained by this expression, where we need only the division by the scalar quantity. And then there's no, you know, matrix inversion is used in this, you know, calculation, right? So, you know, remember pt is actually inverse to this matrix. And then actually, in a previous, you know, pt minus 1 is basically updated to new pt through this equation without taking the inverse. So that's actually cool stuff. This particular expression is actually, you know, one of the special, you know, cases. You know, now it's known as matrix inversion lemma. And, you know, Max Woodbury, you know, found the more generalized version. So we derived this expression by using the particular, you know, structure of the matrix pt, but it doesn't have to be in that way. Well, actually, this is the more general matrix inversion lemma. If you substitute the, you know, pt minus 1 to A inverse, and so A is actually pt minus 1 inverse, you get basically the same equations. You can check it on your own. Now, here, I know our case, you know, B is V, and then C is 1, and then D is phi transpose. But you know, it doesn't have to be this way. You know, C must be an invertible non-singular matrix, and the B and the D must be you know, consistent dimension matrices. Other than that, it's arbitrary. So this is more generalized the case. Yeah. So this is actually matrix inversion lemma. So the final step that we need to do is that you know, well, we'd like to find the you know, this, you know, the optimum ones. This one should be written, you know, in a recursive form like this. This is something, you know, we originally you know, considered. But you know, in here, more specifically, we'd like to consider this particular form. Here, if you look at the yt minus y hat, what is this guy? This one, yt is the real observation. Y hat is the prediction based on the current best knowledge about the parameter theta hat, you know, and which is known at time t minus 1, right? So we create the predictions in y hat based on this parameter, you know, value, and then make a comparison against the actual measured one. So this is the prediction error, okay? So we do some kind of a negative feedback, to this actually estimate with this gain KT. And we like to find the optimal gain that is to guarantee that the theta LST obtained in this way is exactly the same one as the correct, optimal, value, okay? So we have two goals to show that this one is given by this. Remember that the PT times BT is the optimum solution, right? So BT is basically summation phi times Y, and the PT is inverse of the matrix phi transpose summation. Okay, so we like to show this, and also we like to find the particular gain KT. So let's do that. So we start with these two terms, so let's find the difference between the two. And by definition, theta LST must be this guy, right? PT, BT. And then one time step back is PT minus 1, BT minus 1, right? So PT, let's replace this one by using that matrix inversion lemma expanded to this expressions, right? Remember this guy, right? We obtained. And then BT is expanded to BT minus 1 plus remaining part, new data here. And then we just leave this one here. And interesting, and this PT minus 1 BT cancels, when you expand this, leaving this part, T minus 1 times this guy, and then this times this, that shows up in here. Just for brevity, I omitted parenthesis T, so you can see it in a more simple way, right? So let's compute this. Okay, just writing the same equation over here again. Now we have theta T, PT minus 1 Y phi blah blah blah. Now actually through the reduction of fraction to our common denominator, we left these terms to the numerator side by multiplying this. So 1 times this becomes this, and this times this becomes these terms, and this part is just I just distribute this one to 2 terms like this. Now, if you examine this term and this terms are so close. Only the difference is that the location of Y is different. But remember, we are dealing with the single output. The Y is a scalar quantity. So scalar quantity can be placed anywhere, right? So you can shift the Y to this position, resulting, this expression, basically the same as this. So we can cancel out these. So remaining, 2 terms of this one, this, and again, the Y is to be placed here. And we have PT minus 1 phi. And after kick out this guy Y here, we have a PT minus 1 phi. So let's factor out this guy in here. Okay, so remember, remaining part is YT minus, phi transpose PT minus 1, BT minus 1. And let's actually, examine this. First of all, what is this guy? Just think about it. What is this? And then divide, times the theta phi transpose. This guy is the optimal value at the time t minus 1, remember, right? Theta ls t minus 1, right? And what happens if you multiply this, parameter vector with the, transpose of your regressor, basically inner product between these two, that's basically your prediction. So what is this guy, YT minus this? This is nothing but prediction error. Prediction error times this again is to give you the difference between these two, which means basically how much you need to, add or correct to the previous one. So what you get is, this expression. So this is nothing but the, LST minus 1. And I put this one here. This one is a prediction error. right? So we can write this guy to be y hat t theta L t minus 1. Okay, so compared to this and to the original, the goal of this analysis, we like to find how much this previous one is to be corrected and updated to get the new one. And we like to see that the correction is to be proportional to the prediction error, just exactly like this, and then multiplied by some specific gain, KT. Now we know this is, gain KT, so KT is this, and, PT can be computed recursively through this. So this is basically to conclude the algorithms, right? So again, previous estimate is to be corrected incrementally by based on the prediction error multiplied by this. But the good thing is that this way, we obtained this theta at the t is basically the same as the optimal one. Okay. So so this is the recursive least square algorithms. So this is the main update row and then gain and then update of the P matrix, right? Now this is the recursive. So starting with the T equal 1, 2, 3, but when you start with the T equal 1, you have to know T minus 1. That is actually 0, right? Theta and LS 0 must be known. So that you have to provide initially. Okay, I can suggest the two methods in providing the initial conditions. One is that you collect the initial set of data. So if you do some preliminary test and you collect the total n samples and data points, so this is the input or regressor, and then this is the corresponding output. You just collect the capital N set of input-output data, right? So with this, you can construct the V naught and the P naught. So Y and the phi, take the product and summation. That's actually B, right? And we use this one as initial B, and then take this inverse. We assume this guy to be good enough to take the inverse, and the P naught is obtained. So theta LS at the time t equals 0 can be provided by P naught inverse times B naught, and we provide this as the initial condition. And with this, you can continue to compute this one, and ever since, always whenever you get the new data point, it is basically you get the optimal one by including the new data. However, this guy requires something in a preliminary test and a lot of annoying, and in some situations it's not feasible to do. So we can actually use some shortcut. And this method is to actually, always make the best corrections, right? So, even though you start with the wrong, inaccurate, or just the guesswork of theta naught, it goes well. Even though you set the 0 for this initial, estimate, that's okay. So shown here is one actually just schematic. So real actually true theta, as you have more data in the data, it's actually changed to this way. And you start with the just a rough estimate. In this case, very rough to be all 0. It can catch up with it, and then actually at the end it's converging to this. Yeah, but to guarantee convergence, we need a little bit more conditions that the P naught originally must be a positive definite matrix, such as the identity matrix. You don't have to be any specific values, but just to take the positive definite matrix that's actually good enough to guarantee the convergence. So usually people take the identity matrix, sometimes multiply by some scalar over here, but that's actually the things that just a minor improvement. Well, next lecture, this coming Monday next week, we discussed a little bit more actually converging, properties and how we can improve this, and a little bit of actual discussion will be made, and also we make a more physical interpretation of this matrix P, and then it's actually recursive, update law. What that really means, and this one is kind of weird stuff. The derivations I've gone through step by step is a very straightforward, simple. But at the end, it's a surprising result. So what really physically means, and that's an important questions. So we discuss that the next time, right? So it turns out that this guy, this particular algorithms, in a little bit more primitive form, was first discovered by Gauss by early 19th century, and some said that according to some literature, he found the original very rudimentary version when he was a teenager. So obviously he's a very great guy. This one has set the kind of a baseline, as I said in the last lectures, Kalman filters are very similar to this in a sense, and this type of recursive formulations has immense impact and then usefulness in many areas. So that is the things I'd like to talk about today. So yeah, let's actually take any questions. So anyone having any clarifications, questions on this stuff?
I had a question from back when we were talking about the least squares estimate.
Prof. Asada, can you hear us?
Yeah, so one question, and John Bell asking for LSE, the regressor data, phi t, the basis vectors for the aggregate matrix. Yes, right. So yeah, to be able to invert that summation phi transpose. Yeah, the collection of phi vectors should be actually the basis and the spanning whole m-dimensional space. Yeah, that's the linear algebra behind it. Yep. Okay, the interesting questions. Bridgie, what if we take more number of measurements than the parameters we are trying to find? More measurement than the number. So if you have more measurements, basically you have more equation to fit, right? So if you think about the type of simultaneous linear equations, linear simultaneous equations, each measurement provides some constraint, right? Constraint that the linear expression must be satisfied. So if you have more data than actually the number of parameters, you face the over-constraining problem, right? Over-constraining problem. So you cannot actually satisfy all the constraints at the same time. Rather, what you can do is to best fit, that's basically least square errors. Fitting that one to the data points, you get the error to here and here and here, right? And all together, that is to be a minimum. So that's actually a minimum stuff. if you are actually more knowledgeable about the linear algebra, like pseudo-inverse, but basically this is a pseudo-inverse case. Yeah, there's no solutions, so the best solution is to minimize the error, squared error. That's the mathematics behind this. Okay, John, you have some questions, whatever? John, go ahead.
You answered my question.
John? John, are you writing or telling? Oh, okay, so that's good. Okay, good. So this kind of recursive least square is very cool. Yeah, and then we, common filtering is somewhat, very different mathematical derivations, but end up with the very similar forms. And other recursive forms too. Yeah, but this is known since the end of the 18th century. That's really surprising. Okay, now what I'd like to do is I want to show you a few more materials which I posted. Let me see. Okay. So this is actually a PS number 1. Okay. We released today, and the due date, you have plenty of time, the 21st. So not in this coming Monday, but in the next Monday, right? Am I correct? Yeah. Monday, September 21st. And I'd like to discuss this one with you at the study group meetings, September 18th. Okay, so typically, problem set to start with the very, very simple, straightforward questions. And just plug in numbers, you get some results. But I know to plug in, you need to understand the, and the notations and the equations, right? Mm-hmm. So the first question is given these 4 sample points, regressor and 3, 2, and then output y is 6, right? 4 data points, okay? So obtain the least square estimate of parameter the theta 1 and theta 2 associated with the this phi1, phi2, right? So you can find this, okay? That is not the difficult problem because just m equal 2, it's a low dimensional. Yeah, very, very simple. So for this kind of a typical questions, I discourage you to use any computing tools. Hand calculation is highly recommended. Yeah, this is the just once a life experience. You don't have to do this twice in your life, But I know when you first learn some new principle, you better do it by hand, right? In particular, the second half of the question. Suppose an additional measurement, phi1 2, phi2 2, and then y equals 3. Okay, this is just obtained. Find the revised estimate with the 2 methods. One is actually batch processing. So this number 5 measurement, you just add this one to this, the tables, and you do the same to compute the theta 1, theta 2. The other way is to be based on recursive least square algorithms. So based on the 4 samples, you got the previous best estimate, right? Theta hat to t minus 1. Okay. Now you get the number 5, a new measurement just obtained. So you can record, you can apply that recursive least squares, right? To plug in certain things into that, you can find the new value, which must be the same as the batch processing result. So this is the hand calculation I encourage you to do. That make sense, right? It's a simple. Okay, the second, the following 2 problem 2 and the problem 3 are slightly more challenging. And this problem too, here's the actually kind of robotics problem or ocean engineering problem. You have a ship over here, and then 3 kind of sensor observation stations located at this particular point on the equity, this triangle locations. Distance is actually L, separated. This XY position versus these 3 reading, alpha 1, alpha 2, alpha 3. Of course, L is actually involved as a known parameter. Okay. So unknown parameter is actually X and Y. And then we like to find the expression where XY are linearly involved in that equation. Again, actually, XY are the parameters we like to estimate, and measurements are alpha 1, alpha 2, alpha 3. Okay. Oh, but by the way, this one is I just used the measurement angular measurement in the all right hand sense, but this guy is moving other way, clockwise direction. So this is a minus. Okay, it should be written in this way, but the same thing, minus in this direction. Okay. Other than that, consistent notation. So if you write out the sum equation, just representing the relationship, algebraic geometric relationship among these variables, first look, you don't see the linear expressions where parameters to obtain are not linearly involved. But trigonometric equations, you can manipulate this, equations, right? So if you manipulate that in some way, boom, you can find the expression where unknown parameters are linearly involved in that equation. I'm not requesting to solve that one, but just show me the linear equation, linear regressor, excuse me, linear regressor where parameters are linearly involved. Okay, are these questions clear? What you need to do? Problem 3 is actually a little complex, messy equations involved here. This is taken from a robotic manipulator arm and robot dynamics. So here's the 2-link robot having its mass parameters. This is actually a planar robot, just moving within the XY plane. And we have 2 actuators. One is the actuator sitting here to drive the first link, and the second actuator is here driving this joint, rotating this second link. Okay, and the robot is to pick something unknown object over here. Okay, including that the mass added to the final link. The second link mass properties are such that the mass of the second link and total mass is m2, and the location of the center of mass of the second link is at the distance LC2 from this joint. Okay, and center of mass is here, and then centroidal moment of inertia is basically I2. Okay, first link is simple. Mass is m1, and center of mass is existing at LC1, and then that's I1. Okay, if you put together the so-called Lagrange's equation of motions, or whatever the Lagrange equation of motions, you end up with this equation. Torque applied generated by the actuator turn 1 is influence the systems in this way, and the Q1, Q2 are so-called joint displacement. The Q1 is this angle, the Q2 is from the extension of link 1 to link 2, so Q2 is this angle. And the torque generated by the actuator 1 is tau 1, and the torque generated by the actuator 2 is tau 2. So how they are related? It's basically related by these two equation of motion. Okay, equation of motion. Here, H11, H12 are inertial matrix components as shown here, which are basically functions of many mass parameters, such as the link1, the mass M1, M2, and the moment of inertia I1, I2. Further, LC1 is the location of the center of mass of link 1, and it also depends on the the bending angle of this elbow joint. The second link Q2 is involved here. It's a really, really messy equations, right? So hard to believe. It's very messy equations. And here dynamic equations too, you see Q2 dot square. It's highly nonlinear. And the Q1 dot, the Q2 dot, it's product of two joint velocities are involved here. It's called the Coriolis effect, and this is a centrifugal effect. This is not the robotics subject, so you don't care this. But what you care is that even though you have a very complex equations, but you can basically manipulate the equations so that unknown mass parameters are linearly involved in these two equations. Now, in this context, what you care is that the robot actually doesn't know its own mass properties. In particular, when it grasps some unknown object, right, which is to change the total mass of link 2, and then also changes the center of mass LC2 may shift somewhere, right? I2 also changes. Yeah, this part doesn't change, but this is the main part. It's heavily involved in these equations. You see M2, LC2, everything that changes, right? So what we like to do is to estimate these parameters when the robot is shaking arms, moving around the things, and then the robot measures how much velocity accelerations and how much torque applied, and respond to that, how much velocity and acceleration it experienced. So collecting these data, the robot should be able to find what is the mass, grasped at the tip, and based on that, estimated parameters, robot can actually adaptively, control its, motion very effectively. So suggested parameters, it's basically, this is the key, hint of this question. Instead, actually, estimate the LC2, for instance, as the location of the center of mass of link 2. Directly, don't try to directly estimate LC2. Multiplied by M2. M2 times the LC2, and then replace that one by parameter, unknown parameter B2. Likewise, M2 is replaced by B1, by itself, but B3 is actually combinations of these parameters, and B4 still in a combination of these actually parameters. If you combine this in this way, you get the parameter vector B1, 2, 3, 4. Okay. Then, interestingly, that the dynamic equation can be written in this way. For the first equation, you remember that the first equation is a very lengthy equations and parameter involved in this as written over here. It's all involved here. Turns out that this equation, can be written in this way. Tau 1 equal some regressor vector phi1 times, I'm sorry, this is a little misleading notation, but phi1 in this case, we have actually, two sets of, regressors. So, one is actually phi1, the other is phi2. And, same theta is involved here, and both equations can be written in a linear regression. So this is very simple. And actually, linear recursively scales can be applied. And then actually, through a real-time control, robot shaking their arm, and it can figure out its own mass. Yeah, so that's actually one of the work studied in robotics to make the robots very adaptive. The final problem 4 is a little bit actually extension of the recursive least squares we discussed. If you check this equation, very similar to the one that we studied. Only the difference is that this denominator, there's no 1 plus, right? 1 was added to this. There's no such things over here. And then this turns out to be a very interesting algorithms. And there's some pros and cons. And so that is something you'd like to figure out, okay? This is actually called an orthogonal projection algorithms. It's a little bit different from recursive least squares. Okay, so these are the stuff we have for the first problem set, and please start working on that. And then let me see. Let me see. Okay. Yeah, this slide. Yeah, can you see the my lecture note? This is full text in the lecture note. In addition to video, you can take a look at this. Okay, very similar story, but you can see it, in a real text. So please make use of it. Okay, so based on this, I think you have plenty of materials to study. And on 18th, this coming Friday, we just have a get together, the first one, a kickoff meeting. And the following Friday, 18th, small group, we like to discuss these actually, problem sets. Okay, I suggest the last 2 questions are maybe a little bit more involved. So I know it's a good materials for your group discussion, right? So that's the things I suggest. Okay, any questions? Okay. Oh, that's Recursive square to have. Oh yeah. The very good question. The Blake code, yeah, that the recursive least squares have some memory in the event that the relationship you would like to estimate is time blind. A great question. This is exactly the topic we discussed this coming Monday. So a situation may fluctuate and changes and over time, how this recursive least squares can adapt to that. That's actually exactly the topic we like to discuss. Yeah. I'll look at some of the chat questions and then respond to you guys. Yeah. Okay, with that, I'd like to close out today's lecture. Okay? Yep. Okay, take care. Bye.
Thank you. Thank you.